Okay, ladies and gentlemen, thank you for being here tonight. I'd like to acknowledge my family that's here. Hopefully the grandchildren will not give too much feedback to Granddad during the talk, but really appreciate them being here, appreciate the support of my wife all these years, going to conferences and staying late at work and working on papers and all that sort of stuff. Appreciate all that she has done as well. In my talk today, I'm going to be sharing some of the experiences that we've had in the Energy Research Group collectively, and I'll also be sharing some of my thoughts along the way. Let me just begin by laying out what I see as a significant global engineering challenge for the 21st century. We live a lot with a dependency on oil. 85% of the world's energy supply comes from oil. And over our lifetime and our children's lifetime, another way of powering the globe is going to be required other than oil. So energy efficiency is going to be an important part of the solution. And when we look at each country, what happens in New Zealand is going to play its role. Each country has to contribute. If a small country says, look, I'm only small, I'm less than 1%, don't worry about me. If enough of people do that, then we're not going to get the change happening. Now, just for the sake of simplicity, most people don't know what a petajoule is, but you probably know what a tanker of oil is. So I've translated some of the figures to tankers of oil. So New Zealand's energy supply consists of about 450 tanker loads of oil a year. Now that's not strictly correct, but approximately. The world is living on about 300,000 tanker loads of oil, and they arrive at Marsden Point regularly and get unloaded, and we sort of live off those. Now, when a country wants to improve its energy efficiency, it makes sense to focus on the big energy users. This is the world's largest dairy factory, located in Taranaki. It uses about 2 tanker loads of oil energy equivalent per year. Now, what's interesting is when you compare that with Hamilton, you find that all the homes in Hamilton will use about that amount of energy, approximately. Okay, so where you make changes at one of the large energy users, it can have a big effect. Now, the politicians sign documents that say we're going to meet certain requirements. They say that we're going to improve our energy efficiency. But how is that going to happen? The engineers are going to play a key role, and the devil is in the detail of exactly how that's going to happen. Now, let me just talk a moment about the Waikato Energy Research Group and some of the important people that have helped to make this possible. Let me acknowledge Professor Peter Camp, who actually started this in the 90s with his research in the oil and gas geology area. In the early 2000s, he helped us get some work going in the industrial energy efficiency area with James Neal and then later Martin Atkins and Lance Wong, helping to form our group. We've also had PhD students over the years. These are 3 of the ones that we have at the moment. We've had final year students working on projects related to energy efficiency. We've had international students, mainly from Europe. These are 3 from Germany and 1 from the UK. And we've also formed international collaboration with world-leading research groups in the process integration area. And collectively, a lot of what we've been able to learn has been a team effort, both locally and also internationally, through attending conferences around the world and presenting papers in the literature. Now, the research philosophy which we adopted in the Energy Research Group was one where we wanted to make a difference in New Zealand industry. We understood that there's a tension at times between research and science excellence at a university level and being able to make a difference in an industrial setting. Okay, both of those things provide a tension. And so one of the approaches that we took was to have a strong industry focus, and James Neal was a key part of that. Had a strong interest in seeing things happen in industry, and so he helped to lead us and get us doing stuff up here and not just sitting in our comfortable locations of the office and the lab and the computer room. And there we were able to get data fed back to us. So what we worked on was real problems, not just imaginary things that academics like to dream up. So practical engineering solutions was something that we endeavoured to do. We also set up relationships with industrial producers and suppliers. And once again, James Neal's interest in the practical side helped to lead that. And overall, we were interested in influencing industry best practice and ultimately changing what was seen as standard practice. So with some of the partnerships, clearly the large energy users are ones that are worth focusing on because some gains there can have lots of benefits. Understanding the government organisations and where the funding comes from was another key part of what we've done. Forming close partnerships with local manufacturers and with the industrial equipment suppliers was all important as well. Now, when we think about engineering research, there's a subject area known as pinch analysis. It's a part of the research that we've done. It became clear that in order to get something that's initiated at the university all the way up to a technology rollout in industry is not an easy exercise. Industry rollout is sort of a great goal. But where we start is way down here at the fundamental research end. And there's a long journey from point 1 to point 6. Some of the things that you might do along the way is you might do some lab scale experiments that mimic what happens in the plant. You might do some numerical analysis on the computer and digital and spreadsheet optimization to give you an idea of what happens on a larger scale in a plant. But a lot of these activities actually converge and lead you to a pinch point. And a lot of university research and a lot of the papers that you will read never really get beyond that point right there. A critical step has to be undertaken, and that is you've got to convince industry to do something in their plant, in the case of the process industry, so they can see firsthand that some benefits can come. If you can get a pilot plant installation, then there's a chance of a full scale. If you can prove that that can work, then there's a chance for technology rollout. So that was something that we saw very early on was needed in order to have the lofty goal of making a difference in New Zealand industry. Now, when you consider where does the money come from to make these things possible, if we look at government funding, what you notice is most of the funding actually gets channeled below the pinch point at the university in the fundamental end. And there's some funding channeling above the pinch to help industry, to encourage it to do R&D, and where there is national strategic initiatives, there may be some funding there. When you look at industry, a lot of people will say industry doesn't fund enough research. What the problem is there is sometimes we're looking in the wrong place. What we're looking at is they're not funding enough research for us down here, but they can actually be putting a lot of money into making changes up there, which are making a difference. And so both of those things need to be taken into account when you think about what is needed to make a real difference. So let me discuss the New Zealand dairy industry that we've been working in as a bit of a case study. I'm only going to focus on one particular initiative that we worked on. There's numerous others that my other colleagues can talk about at length. But when we talk about the New Zealand dairy industry, it's one of the export successes of New Zealand. New Zealand is an export country. If we want plasma TVs, then we need to export things and buy those things in. So about $58.7 billion were the export earnings in 2017. Dairy was $14 billion, or about 26% of that. Now, what a lot of people don't realise is that we actually turn 95% of our milk into exportable dairy products, of which a large amount of that, about 75%, is milk powder products. Now, clearly, to make milk powder requires a lot of energy because you have to evaporate off the water to make the powder. So it's not surprising when we look at the New Zealand industries and we look at how much energy they need for process heat. The food sector is one of the largest at 42.2 petajoules, and dairy is a big chunk of that process heat requirement. Now, why is so much process heat needed? Well, let's have a look at the milk powder production process. It's a simple three-step process. We start off with a big supply of milk, and initially there'll be some pasteurization. We might standardize the milk. We may even separate out the cream if we're going to make skim milk powder. But there's that initial process step. After that, we send the milk to a set of evaporators where we concentrate the milk up to over 50% solids, and then we feed into the spray dryers. A large amount of steam is required to heat up the air, to then drive off most of the water to where we end up with a product that's essentially dry at 96% solids. So this process has been around for quite a few years. So how can we improve the energy efficiency of something that's been around for so long? It's not an easy task. Human nature has it that we'll often improve over time, so we're arriving late on the scene. How are we going to improve it? So here is an interesting diagram. The exact numbers have been removed, but it tells a story. The height of these bars represent the energy per tonne of milk powder produced, the specific energy at a range of factories built in New Zealand over a number of years. A high figure means we're using a lot of energy. A low figure means it's more energy efficient. So what you notice is there's been an improvement over the years, and now we've sort of plateaued off. Have we plateaued off because that's the best we can do, or is there some other opportunities that still need to be determined? So one of the tasks that we needed to determine was, is there room for improvement? We believed that there was, so we set a goal of a 30% improvement to milk powder production in New Zealand and began to look at the research pyramid, the engineering research pyramid, as I've called it, and we said, what are all the projects that we need to do to feed in at the bottom of the pyramid in order to reach our goal of 30% improvement? Now, not all of these projects are going to necessarily bear fruit, but they may well help us on the journey. Now, from an academic research point of view, we looked to some of the thermodynamic theory to find out what were the limits of heat exchange that was possible to share exhaust heat with some of the streams that needed to be heated. So theory says, yes, we can do it. But when we talk to industry, questions of doubt are raised. Is it really possible? Will it be economic? So this is sort of where sort of theory has to hit with reality. So the work that we did needed to address applying of theory, but also the practical reality of being economic. And that's what engineering research aims to do, to create things that ultimately can lead to products and systems that are economic. The other thing that we were aware of is that industry has practices that they're used to doing, and we're going to have to influence that and change industry practice. So how do we de-risk things so they're more willing to make a change? How do we get the economics to work? If I ask one of the international suppliers to give me a quote, he almost says to himself, I wonder how much we can charge. That's what a free market is like, right? You charge as much as you can get away with. So how do you get the guys to sharpen the pencil? The engineers from the international suppliers to sharpen the pencil and say, hey, we've de-risked the project so as we can get the economics to work. And what is the implementation pathway that's going to make this possible? The other thing that we had to think about was, what are the plant complications? If we're going to provide a solution for the world's largest dairy factory, what things do we not know that we should know that we need to take into account? Well, the first thing was realizing that milk production in New Zealand is not constant. The cows give off milk to supply to the calves, and there's a peak. October and November, there's a large amount of milk that has to be treated, and then at other times in the year, there's a lot less. So what does that mean for the plants? Well, a lot of the plants have multiple factories or multiple processes. They're not running all the time. So anything that you dream up of a scheme to save energy, when you do the cost analysis, you have to be aware of how often the plant's running, which ones are running, and how does that affect the scheme that you're dreaming up. The other thing that happens, you're making a food product. It has to be cleaned regularly. The plants are not always running. They're having to be shut for cleaning purposes, for changing to a different product. So they are semi-continuous operating plants. That adds a level of complication. There's a need for energy storage in any solution that you might be coming up with. The other thing you have to be aware of is fouling and hygiene issues. The slide that you can see on your right is a photograph that we took at 6 o'clock in the morning at the Te Rapa Dairy Factory. Why was a group of academics at the factory at 6 o'clock in the morning? Well, that was when they clean the dryer. That was one of the doors or the hatches to one of the large spray dryers. And this is what happens to it over a number of hours. 12, 16, 24 hours, gets dirty, has to be cleaned. The operators that were there were surprised to see us in the morning. Who are you guys? What are you doing here? We're from Waikato University. Really? We've never seen guys from Waikato, from any university, at 6 o'clock in the morning. Well, you know, James can tell a lot more stories. I think he's been there all night some of the time. But one way to build respect is to be there early in the morning with the operators and seeing them have to keep the plants running and deal with their problems. Not the usual thing for most academics. The other thing that you learn when you're there is that operators have their own culture. And if you don't learn the culture of the company, when you come along with your bright idea, then these guys will say, you're a dreamer. It won't work. Did you think of this? Did you think of that? Okay, so changing the culture is also a very important part of the process. So having training of operators plays a role. And the Energy Research Group has been involved in some of that activity. So what areas of research do we need to focus on in order to come up with a way to improve the energy efficiency of one of these large plants? Well, here's sort of 4 project areas. that we can have. I'm going to focus down here on 3 and 4. Milk powder fouling and a heat exchanger design that is able to recover heat from the exhaust of the dryer and do some preheating at the inlets. So let's have a more detailed look at a milk spray dryer and how heat recovery can be achieved. So here's a schematic of a spray dryer operation. As you can see in the bottom left-hand corner, we have outside air coming in at 15 degrees. It's heated by steam to over 200 degrees, mixed with milk concentrate at the top of the dryer. And evaporation occurs, milk powder is formed and comes out the bottom, and we end up with hot, warm air exhausting there. Now, it's pretty simple. Take heat from the exhaust and exchange it down there. Well, problem solved. Well, many years ago, 10 to 12 years ago, we looked at this and says, oh, that's simple. But then people start telling you of all the problems. Remember, the devil's in the detail. So what's wrong with doing this? What are the issues that have to be overcome in order to create an economic heat recovery system that's not going to foul, that's not going to just block and stop operating after 6 hours and then we have to turn the plant down and clean it out? So what are the barriers to implementation? Do the barriers give us an idea of what research needs to be done? So clearly, milk powder fouling was of concern. There was the risk of blockage if we were to put some heat exchangers in the exhaust. The last thing the company wants is unplanned shuts. Millions of dollars can be lost quite quickly. It's not standard practice in New Zealand. So, how do we make the change? There might be resistance to change. A number of years ago, 2009, James Neal was visiting a plant in the South Island. It was a new plant being built. There was actually an exhaust heat exchanger that was going to be put into the dryer. The factory got nervous and changed its mind and didn't put the heat exchanger in. And I don't know if it still sits there in the outside, but it was there for a number of years. But the project did not go ahead because of the fears of blockage. So that was another important area. The other one that we found was significant was questionable economics. Was the rate of return good enough for this to go ahead? So with those barriers being understood, we were able to start thinking about what's the university-based research that is needed to help overcome some of those barriers. And if we go back to our engineering research pyramid, we sort of said, what projects do we need to put in there and there and there to enable this to happen? So let me show you some of the projects that we initiated. We had master's students, we had a PhD student, we had fourth-year students work on this. This here is a piece of equipment that we set up in the lab. We could heat up air, we could inject milk powder, the milk powder would be affected by the hot air, and we would shoot it at a plate, and we would look at what were the properties of the air and the milk powder that cause sticking or fouling on stainless steel surfaces. Like true academics, we got excited about the data, we curve fitted, we developed all sorts of fancy models, we wrote papers, we got accolades for good work. Industry never read the paper, but we felt good. So we went to the next stage and we built a small lab-scale fouling test rig. Simply hitting milk powder against a plate was sort of too idealistic. Why don't we see what happens when the milk powder comes in contact with tubes? So this is what's happening here. The milk powder is put in that little port, hot air comes here, moves along, and there's some tubes about this location. We can feed water into the tubes to change the temperature, and here's some of the results. Okay, so on the front and on the back, we could measure how much milk powder was sticking. We could play around with what conditions doesn't cause sticking, what temperature, what airflow rate, and so on. We also looked at finned heat exchangers and looked at when do we get milk powder sticking to the fins. And all of this information was put into a spreadsheet optimization model, so we could then design and make recommendations to an optimal fin tube heat exchanger, which was then made by the local supplier, Windsor. So what we've just done is we've worked our way up the pyramid to this point. And now we're at the critical pinch point. How do we convince industry to do this? To put in a pilot plant. Now, fortunately, we applied for funding before MB changed the way that they run the portfolios, and we successfully wrote a bid that gave us some money with some help from industry to put in a pilot installation. Okay, so a pilot installation was put in the Te Rapa dairy factory on the roof of that main building that you see when you drive past it on the motorway or on State Highway 1. A few months, or probably a year before we did this, a couple of us climbed up to the top of the roof and we happened to see this up there on the roof. This is the exhaust from one of the dryers. It's quite a big exhaust. And this hatch, if you open it up, you can look inside there and you've got air flowing, hot air flowing out. So the idea was, why don't we attach to that hatch and we can put a rig that we can test to see if we get blockage, how much milk powder is going to be caught in the heat exchanger, and we could also monitor the performance of our heat exchanger. So this rig was what was designed. This is the heat exchanger that we're going to test. This is another heat exchanger that we connect with that. That is doing the heating up. That's doing the cooling as part of a water loop. This was the day that the rig was lifted up 50 meters to the top, the roof of the factory, July 2015. This is the rig installed. Here's the various parts. As I said, there's the exhaust. So the hot air is coming down there and out. There's the heat exchanger that we're testing, and this the heat sink heat exchanger. And we had a water loop, so water is pumping around, so we can measure the performance of the heat exchanger. Now, let me just show you some interesting results. The green represents the change in the pressure of the air going through the heat exchanger. After 42 days, there'd been minimal change. The blue represents the performance of the heat exchanger. After 42 days, once again, minimal change. So there hadn't been any effect at all. Basically, we were able to confirm what we had worked out in the lab, that if we operate it under certain conditions, we will get no fouling. Industry was a lot more convinced now that we had actually put it in their factory with their milk powder, with their air, etc. Now we had all that we needed to produce an informed business case. We'd already worked out quite some time ago that this approach of extracting the heat from the exhaust of the dryer and recovering it and reusing it to heat the incoming air or any other incoming stream could give us between 10 or 15% energy efficiency improvement. And if you think back to our 30% goal, then it had the potential to be 35 to 50% of our goal, potentially. Different factories have slightly different potential. We showed that you could come up with a system that doesn't have fouling. We also showed that because of the de-risking, you don't need to oversize everything just in case and make it so expensive that it no longer has a good enough rate of return. We can put a bit of pressure on the suppliers to make sure that the business case can work. So essentially we're taking heat from there and feeding it down there with a water loop going round. So just to recap, we've successfully made our way up the pyramid through the pilot stage, and now the group, those that are full-time in the group, are working closely with industry for a full-scale implementation, and we're pretty confident that this will become an industry standard as the industry has signed up to reduce its emissions and hence its energy usage significantly by 2030. The other thing that we've learnt is that there's some differences between academics sitting in their office and industry people, especially in processing plants. This is a little bit of a humorous list, but a lot of academics love to be the first and get lots of citations. If industry is the first, they like to keep it a secret. Or in other cases, they don't want to be the first because it's too risky, which is interesting. Another thing, we love proposing new theories. They want you to keep it simple, especially if you're training operators who ultimately have to implement what you're doing. We like to come up with new methods. They're quite satisfied staying with what's tried and true. We love theoretical and simplified studies. We like to make sure it's a confined problem. They want us to do real plant studies with all of the complication. So that way what we suggest actually is real. Academics in their office are always optimistic with costs. Industry people often are very pessimistic with costs. They know what the cost of the change will be. In any costing, it's what you leave out that's the biggest source of error. And once again, in your office, you don't know what you don't know. And that's the biggest source of error. The other thing here is we're often not aware of the worst case and the problems that arise periodically that we don't take into account. We're often less time and money sensitive. To us, yes, we'd love to do the project. Here, we'll give it to the student. They can work on it for the next couple of years. Meanwhile, industry wants it solved next week because it's costing them. And lastly, publish, 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 production, production, production. So how do you work with industry when we have these different needs, these different drivers? Well, one of the things that we've found is you've got to build trust. A trust between the research group and the industry partner is key, and having people in the research group that are willing to spend time with the industry partners is a really key part. And lastly, there are many engineering challenges that benefit from university-industry partnerships, but they do require vice-chancellors and university leaders to understand the difference between scientific research and engineering research, which is not just interested in fundamentals, but is interested in forcing its way through the pinch point and making a real difference in industry. Thank you very much for listening.